So, hello everyone. I'm so glad to be with you for the second year. I wish you all are doing well. Today will be the start of one of 8 sessions or lectures that I will be with you through this summer training. Today we will talk about unlocking hydrocarbon resources, in which I will give you an introduction to the petroleum geology and applied geophysics. So our agenda for the lecture today is what I mean will be in 2 different places. One of them is, because I'm a geoscientist, so it will start from the subsurface, and then we'll go to the ground surface. From within the subsurface, we will cover the hydrocarbons and geosciences, the relation between these, what we want at geoscience from the hydrocarbon. And then we will give you what is a rock, what is petroleum in general, and we'll give you some information about the petroleum business, followed by the petroleum system. Then when we finish this, we will go on the ground or on the surface of the earth, and we will see how we can find out all of this subsurface information. So we will talk about the geophysics in general. So what are the goals of geophysics? Then I will talk about the magnetic method, the gravity method, the seismic method. I'll give you hints about the well logs, because you are gonna study that, what I mean, in more details. And then I will give you also a hint about the seismic and log example. So within the subsurface, we'll talk about hydrocarbon and geoscience. So what is a petroleum geoscientist looking for? So actually, he's looking for oil and gas reservoir. And the reservoir is a rock, is a type of rock. So does this reservoir a pool or a cave? No, it's actually a rock formation, like a sponge that contains a hydrocarbon in a large quantity. Or what's the rock? So the rock is defined as any naturally occurring solid mass or aggregate of one or more minerals. So we can have rocks forming of one mineral or native mineral, so, or we have mix of minerals, as you see in this picture here. So we have, this is a sort of type of rock called granite. So we have potassium feldspars, we have quartz, we have pyrrhotite. Each one of them is a different mineral. For example, as you see here, this is quartz crystal, for example. So mineral is built up of crystals. The petroleum system and most oil and gas production occur in type of rocks that we are gonna talk about it in details now. It is called the sedimentary rocks. Why the mineral is important? Because the type of mineral present in a rock influences its chemical stability, and thus its stability as a reservoir rock. Okay, so let's see. So are all rocks of the same type? No, we have 3 main types of rocks. The first one is the igneous rock, and in igneous rock, this is a picture of the rock called granite. So these rocks are formed, or the source of material of these rocks are the molten material in the deep crust and the upper mantle, and the rock is forming from crystallization or solidification of this metal. The second type is a sedimentary rock, and the most famous rock of the sedimentary type is the sand or the sandstone. We call sand as a sediment, and when it is solidified, we call it as sandstone. These type of rocks, which is the sedimentary rocks in general, are forming due to the source material for it is the weathering of the rocks and erosion of the rocks which exposed to the surface of the earth, and it is formed by deposition. And the deposition of sedimentary rocks are found in basins that we are going to talk about basins in a minute. The third type of rocks is a metamorphic. The metamorphic rock could be originally a sedimentary or an igneous rock, but it exposed to very high temperature and pressure in the deep crust, so it is recrystallized due to this heat and pressure and form a new type of rock. Okay, which one of them is important for petroleum accumulation? We just mentioned in the previous slide. So the sedimentary rock provides the hydrocarbon source rocks and most of the oil and gas reservoir rocks. So sedimentary rocks formed the source of petroleum rock and the reservoir. The igneous rock are of minor importance actually in oil exploration because it doesn't have neither have organic material nor have like porosity or permeability, as we'll talk about later. But it is rarely can form a reservoir when it is like fractured due to whatever any type of weathering. So if I have a fractured igneous rock in the subsurface, so it can act as a reservoir. The last or the third type of rocks, which is a metamorphic rocks, actually in this type of rock there is very little organic matter or hydrocarbons due to the high temperature and pressure. So the most important rock for us in the petroleum industry is the sedimentary rocks, and this is what we usually are looking for. So the main types and relative abundance of these sedimentary rocks, we have a type called siltstone, mudstone, and shale, and this type of rocks form about 75% of the sedimentary rocks all over the world or in the Earth's crust. And we have the second type, or after that is the sandstone and conglomerate, which comprise about 11% only of the sedimentary rocks. And then finally the carbonate rocks, which are either limestone or dolomite, and they represent about 13% of this type of rocks. So we have these types of sedimentary rocks are sandstone, the most famous, conglomerate, siltstone, mud and shale, and limestone and dolomite. So let's see what's petroleum. So we know that different types of rocks now, and we want to know what is petroleum. I know that most of you know that, but just to remind you. So petroleum is a general term for all naturally occurring hydrocarbons. And hydrocarbons is built up of hydrogen and carbon. If this hydrocarbon is solid, so it's called asphalt. If it is liquid hydrocarbon, it's called crude oil. And if it is like gas hydrocarbon, it's called the natural gas. And the most famous natural gas are the methane, butane, and propane. And what you see here is the simplest hydrocarbon, which is the methane, the CH4 component. So let me give you some terms in the petroleum business to understand what we are talking about. So we pass through different stages or steps, which is started by the exploration, followed by development and production, and then by refining and desealing the hydrocarbon materials that we extracted from the earth. So at the beginning, in the exploration and development phase, the geology is very important, but economy is less important because we'd like to find hydrocarbon. Okay, this is the main aim. So because of that, geology is very important. But when I go to refining and sale, so economy is more important than geology, but geology is less important in this case. Some of the terms also in the business is the exploration and the production stages or phases. We call it the upstream, and the refining and sale, we call it the downstream. So we have upstream, downstream. What about the midstream? The midstream sector involves the transportation, storage, and wholesale marketing of crude or refined petroleum products. So the important elements is know where to search, where I can find the petroleum accumulation, know what to look for, what I mean tools to use for that, okay, and then recognize that this is hydrocarbon trap or hydrocarbon accumulation when I find it. When I see it, I can say that this is a hydrocarbon trap. So we have three main work phases. The first one is the exploration, and we mentioned that geology is very important in this case or this stage. So for exploration, we have geophysics. We can apply geological applications. For geophysics, we use seismic acquisition, processing, interpretation. We can use gravity and magnetics, as we will show later. In geology, we working with the basin analysis, basin modeling, and we can do some quantitative assessment. Some of the disciplines used, like we look for the tectonics, what's the structural setting of the subsurface, what's the depositional setting. We're talking about stratigraphy, reservoir distribution, reservoir parameters, source rock distribution, hydrocarbon generation. I will give you hints about each of these. What about migration of oil and the well prognosis? In this, we use geoscience tools like geochemistry, in addition to the geophysics, geochemistry, petrophysics, stratigraphy, prospect evaluation, and risk assessment. In the development phase, we still have the geology, we still have the geophysics, we will have a bigger role for the petrophysics and the geochemistry, okay, and then we can build a 3D stratigraphic framework model, and then we integrate all of this data and do reservoir simulation and so on. In the production phase, we have the engineering, production monitoring, the fluid flow rates, and the completion strategy and whatever. And then we can use also the geoscience. In this case, we can use the 4D seismic, for example, to find out the oils that we didn't reach to it, or if we have compartments in the reservoir, how we can find it. Also in geology, we have field studies and whatever. And as you see, we have also reservoir simulation. So to understand or to more understand the petroleum geology, we have to know about the petroleum systems. In petroleum systems, we will start with the levels of petroleum system. So we should have a sedimentary basin. So when we explore for hydrocarbon, we're looking for the basins. What basins? I will show you how the basin is looked. But basin
is a low area that can accommodate the deposition of sedimentary rocks. Okay, so to start what I mean, hydrocarbon exploration, I look for basins at the beginning, and it is a sedimentary basins. Again, because sedimentary rocks are formed by deposition of the weathered material, and this deposition should have a place to accommodate them, which is the basin. There are different types of basins. How can these basins are formed geologically? There are different types, but today we are talking about like an introduction. So I'm looking for sedimentary basins. This is followed by, does the petroleum system works in this basin? So if I found the basin or the sedimentary basin, is the petroleum system okay, or does it work? We will see that now. And then I will find a play. A play is a place that I will drill, or what I mean, I can choose for drill or test to explore it. Then this play, I can, what I mean, upgrade it to a prospect. The prospect is what I mean when I have more confidence that this will be oil accumulation or gas accumulation, in general hydrocarbon accumulation, depends on the data, the available data, and whatever. Then I have to find out the formation of petroleum. So how petroleum is formed? So we should have a supply of organic material in the past, in the history, in the geologic history. So if I have the basin and I have sedimentary rocks, so there was like a supply of organic material or not in this basin? Is there sediment supply or not? And then we'll see if I have sediment supply and I have organic material, enough organic material, I will end up with a rich source rock. If this rich source rock is a sedimentary rock rich in organic material. If it is supposed to heat and pressure, then I will have a formation of hydrocarbon or petroleum in general. So the petroleum system exists wherever the essential elements and the processes occur. What are the elements and processes? The elements of the petroleum system are the source rock, the reservoir rock, the seed rock, and the overburden rock. So when I look for a petroleum system, this is the characteristics of the petroleum system. I should have these four elements present, and I can study them well with the tools that I just showed you in the previous, or the slide before the previous one. Then the processes to form the hydrocarbon are the trap formation. I have to have a trap to prevent the hydrocarbon from escaping to the surface. The generation of petroleum, the migration of petroleum, and the accumulation of petroleum. So for the petroleum system, I should have some elements, or four elements, and four processes. The four elements again are the source rock, reservoir rocks, seed rock, overburden rock. And the processes are the trap formation, generation of petroleum, migration of petroleum, and the accumulation of petroleum. All of these essential elements and the processes are important for a petroleum system existence. So let's take the elements and talk about them to understand more what about them. The first one is the source rock. And this picture is for the shale, which is type of the source rock. So the source rock is defined as a fine-grained sediment, contains sufficient amount of organic material, okay, and can generate and release enough hydrocarbon to form a commercial accumulation of petroleum or for oil and gas. Sedimentary rocks by deposition or by are rich in organic material. About 0.5 to 2% of its weight are usually formed of organic material. The organic material are not, the organic material is, what I mean generally is a microscopic marine material in some origin or some type of oil or gas. Even we have organic material that have an onshore origin. Okay, and this material, when it decay, it left some carbon. The second element is reservoir rock. And the reservoir rock, as we mentioned before, it's like a sponge. It is a type of sedimentary rock that contains porosity and permeability. Porosity is pores or pore and throats between its particles. And this is one characteristic of the sedimentary rock. So any rock that contains porosity and permeability is a connection between these pores. So if there are pores and they are connected, this type of rock will act as a reservoir rock. And it is mostly from sedimentary rocks. And as we said, if we have fractured igneous rock, it can act as a reservoir. So if you take a look on this synthetic section here, this is from a real reservoir rock. So the reddish color is for particles, rock particles, and the oil is the black one. After that, we'll talk about the seal rock and overburden rock. The seal rock is the vice versa of the reservoir rock. It's a type of rock. It could be a sedimentary or any other type of rocks, but it is impervious. Okay, so it has no porosity or permeability. Okay, like for example, the shale rock. So the shale rock can act as a reservoir, can act as a source rock and a seal rock. So shale, anhydrite, salt. Okay, so any impervious rock can work as a cap barrier for the reservoir rock. Then the overburden rock. The overburden rock actually works a very important role because it overlies the source rock, so it pushes it deeper in the earth where is a high temperature and pressure, okay, and reducible environment. So it cause the cooking or the maturation of the organic material within the source rock and to be changed into or converted into hydrocarbon. So this is a situation. So you have like the sediment are deposited in the sea bottom, for example. We have some organisms. These organisms are, which is the organic supply. So it is paired with the rocks, and then we have other rocks, which is overburdened until we have the petroleum system. So after that, we will talk about the traps. I will mention two main types of traps. Actually, there are different types of traps. I will mention two of them, the two main types of traps, which is the structural hydrocarbon traps and the stratigraphic hydrocarbon traps. The structural hydrocarbon traps could be like a fold, as you see here. This is a picture of a fold. This is on the surface, for example. This is a fold, could be governed by folds, okay? And these cartoons show that we can have also, so if it is an anticline, we will have the oil and gas entrapped below this seal rock, which is, or impermeable rock, which is a seal rock, or on the folds. It is, if this fold is sealed, what I mean, so closed, it's not a conduit, so we can have like the hydrocarbon accumulated in this one. Also, the salt diapers in the subsurface could form structural traps. So the main key elements of structure trap or any trap actually, we'll mention the same 4 elements in the stratigraphic traps is the reservoir. So I should have so a trap the trap includes a reservoir, a top seal, a base seal, and fold seal. I can add also a lateral seal. So the fold seal here, what I mean is a lateral seal. So I have to have seals from all directions for the trap, to form a trap. So the structure trap is formed by a geological structural element. Then we go to the stratigraphic traps, and the stratigraphic traps are formed by stratigraphic elements like a pinch out, for example, the submarine fan loops, the carbonate buildup, okay? And this is a picture from a surface outcrop, shows the stratigraphic relation between the different types of rocks. Again, the traps, to have a stratigraphic traps, so I should have the reservoir, the top seal, the base seal, and I could have fold seal, actually in the stratigraphic traps or not. Let's talk now about the processes. So the hydrocarbon migration, you know that the oil density is lower than the water density. So water plays great role in the hydrocarbon migration. Because oil is less dense than water, okay, then it moves with the water through a carrier bed from the source rock to the reservoir. Okay, so carrier beds are type of rocks that allow the fluid to pass through them. So how can a rock allow the fluid to pass? It should have porosity and permeability. Sometimes the faults act as a carrier or a conduit for the migration of hydrocarbon. Example of the carrier beds are the sandstone. Okay, if the petroleum stay buried in the source rock, okay, it could be post-mature. But nowadays we have like the shale gas and shale oil. So it's different stories than the hydrocarbon, the fluid, or the hydrocarbon, like the oil and gas. So the hydrocarbon migration, simply it is the movement of oil and gas in the subsurface. We have different types of migration. We have the primary migration, we have the secondary migration, and then the accumulation. So for the primary migration is the movement of the generated hydrocarbon from the low permeability source rock. So this is the source rock, as you see in the figure here. Okay, so it generates the hydrocarbon, and then this is followed by the secondary migration, which is through like the carrier beds or the fault, as you see in this picture. Okay, and then the accumulation when the hydrocarbon concentrated, as you see here, the reddish color here. Okay, this is the accumulation. So it is generated here. It had the primary migration to the source, and then a secondary migration towards the reservoir, and then entrapped under the cap. So generally speaking, if I have this cartoon for the subsurface, if I have like here is the surface, this is some layers of rocks, and we have we call this as a monocline or a limb of an anticline. Okay, if I have like at these depths, this is the top maturity, which means that deeper than this line here, hydrocarbon can be matured or can be formed. So, and also if I have this as a reservoir rock, and I have an impermeable fault, which is called seal fault in this case, and I have the seal. You see, I'm looking for the elements and processes, and this is the seal rock, and this is the source rock. Then the source rock exposed to the heat and pressure, and it start to generate hydrocarbon, and this hydrocarbon primarily migrate from the source rock, and then secondary migrated towards the reservoir, and then accumulated at the crest of the structure, and entrapped because of the seal rock here, which is a lateral seal, and another lateral seal here, which is the fault. And I have here also a cap that prevents this hydrocarbon from escaping towards the surface of the earth. Now we got like some information or introduction to the petroleum geology. So how I can find this petroleum? It is in the subsurface. Now I'm on the surface. I'm on the ground of the surface. We are live on the surface of the earth, not under or beneath the surface of the earth. So how can I find this hydrocarbon accumulation in the subsurface? The best tool is the geophysics tool. This is the best tool to find out the hydrocarbon in the subsurface. So because of that, the geoscientists are these groups that can see beneath the subsurface. Okay, so without a glass, what I mean, we use geophysics to know or to see the underground or beneath the surface. So the geoscientists find out methods which are depends on the physical properties of the rocks. Because of that, it's called geophysical methods. Geophysical because it looks for geology and using the physical properties of the rocks. So generally speaking, the goal of the geophysical methods are imaging the subsurface structure and the stratigraphy, the setting of the stratigraphic and structural setting in the subsurface imaged by the geophysical tools. Okay, so let's know what are the known geophysical methods or famous ones. We have more actually geophysical methods than that, but this is what that are more or less related to the hydrocarbon exploration. So we have the magnetic method, which depend on physical properties called the magnetization. You know the magnet, as I will show you now. The second method called the gravity method, which depends on the density of the rocks. The third one is the seismic, which depends on elasticity. Then the electric method depends on conductivity. The radiometric, radioactivity, and the geothermal, which is working on the thermal conductivity. These three geophysical methods are mostly used for hydrocarbon exploration and especially the seismic method. The other methods are used for hydrocarbon exploration and development, but they are used, what I mean, through logging in the drilled wells and so on. But magnetic, gravity, and seismic methods, we call them the surface geophysical methods. So let's take a look or get some information about each of them. I'll start with the magnetic method. So the magnetic method, we all know the magnets. We all see the magnets. Okay. So the earth itself is has a natural magnetic field. It's a big magnet. The earth itself is a big magnet. Okay, and we have a magnetic also field on the sphere around the earth. So the magnetic techniques, this is a natural technique. What I meant by natural technique is that it measures natural physical characteristics. So the magnetic techniques measure disturbance in the Earth's natural magnetic field. Okay, so what type of rocks is characterized by magnetization or contains magnetic mineral? We mentioned three types of rocks. So the most type of rocks that contains iron oxides and nickel or has the magnetic susceptibility is the basement rocks. Okay, and the basement rocks are the rocks, it's called basement. Basement means that below this basement, there is no sedimentary rocks. So it is the base of all of the rocks. Above this basement rock, we will have the basins that contain the sedimentary rocks and so on. Okay, and so from the magnetic methods, you know that, as I mentioned before, we are looking for basins. Okay, so if I have a basin, so the basement rock should be deeper. So I have a room for a basin to be found and to accommodate sedimentary rocks. But if these basement rocks are very shallow, so there is no chance to have a basin with a thick sedimentary rocks. You got the idea? So I use a magnetic method to know where is the basement rock, the depth and the structure. Because as you see in this one, so you have this reddish color, which is called granite. The granite, as I told you, is type of the igneous rock, which is forming or build the basement. So the basement rock are built up mostly of igneous rock and metamorphic rock. So the basement rock are built up mainly of igneous and metamorphic rocks. Okay, so the granite is one of the igneous rocks, and you see how it looks like a fold here, and all the deposited layers above it, okay, takes the same shape. Also, it can be faulted. So I will have the sedimentary rock in this graben in the middle. I want to have thick sedimentary rocks in the two sides. Okay, so this is the importance of magnetic method, and I use the magnetic method when I explore in a new area, unknown area. So area that doesn't have any subsurface information. So I use the magnetic method, which is cheap compared to seismic, and I can have like models that you see, cross sections as you see like this, or I can have also maps. So from these maps and cross section, again, I identify the basement depth and the structure. When the depth of the basement is big, so I have deep basement rocks, then I will have a room for a basin in which the sedimentary rocks can be deposited. But magnetic methods has another application, a lot of applications actually, but this is what we use only in the hydrocarbon exploration. For the gravity method, as we mentioned, it depends on the density. Actually, the lateral change in density of rocks. To understand that, we measure the gravity acceleration. Suppose we have this subsurface rock in this cartoon, this ridge ball, this is density particles or whatever. So if you took a look, you found that at the middle here you have this body which have denser red balls compared to the surrounding. So if I came from the surface and I throw a ball in each of these different positions, imagine at which locations this ball or will be faster, what I mean, or will touch the earth before the others. Okay, so this is what we measured, or this is what measured in the gravity method. So gravity methods, if you type the curve for this gravity acceleration, you will find this pop here, which is we called anomaly. So this is gravity anomaly. This means that you have a denser rock in this area. Okay, so if we talk about density, let's give you an example. If you have like a salt dome or salt body, which can form structural traps, the density of the salt is much different or much smaller than the surrounding rocks. If you have sedimentary rocks or other types of rocks. Okay, so I can delineate the salt bodies, for example, and then I can know where are the traps. So also sediment, also with the gravity method, I can build like vertical cross sections or maps, and I constrain the salt bodies and locate the basins. So the gravity method gives me a direct direct interpretation to that in this area there is a basin or non-basin. So let's say basin and non-basin. So if I use magnetics and gravity methods, okay, and the magnetics said that the basement is deep in this area, and the gravity confirms that this is a basin. So in this case, my confidence will be much bigger that I have a basin here. Then I will go and apply seismic method, because the seismic method provides the best tool for imaging the subsurface. I can say that there is no hydrocarbon exploration or development without seismic method. So the seismic method is the key for hydrocarbon exploration. Again, gravity methods have more other application than the hydrocarbon. So if we take a look on this picture in front of you, this is a vertical seismic section. We call it 2D seismic section. You see this stratification here. These are a reflectors. This is a basin here. This is a basin where you have a sedimentary rocks. You see this faint amplitude on the two sides. It could be salt intrusion or whatever. I just give you a clue how we interpret seismic data. We have fault here, so this is a sort of basin. You have some faults here that you have like different type or different depths of the reflectors. So this is how we can see the seismic data. So you can see details, lot of details actually within the subsurface. When we talk in the other lectures, you will understand more and more about seismic data. I call the seismic data, or the seismic data is a treasure actually. Seismic data is a treasure. So you can start from having this interpretation, as you see in front of you, from just the reflectors that represent the subsurface structure and stratigraphy, up to changing this picture into fluid distribution and mineral types, lithology and fluids. Also, you can extract from seismic the geophysical parameters, the V shale, the water saturation, the hydrocarbon saturation, whatever. We will see that in the coming lectures. So, to do seismic, we have three main stages. We will talk about each of them in the coming lectures alone. So we'll have the seismic data acquisition, the seismic data processing, followed by seismic data processing, and then followed by the seismic data interpretation. So what is the seismic method? It depends on what? It depends on sound wave propagation. So we send sound waves to the subsurface. You know the echo? All of us, experience the echo. When you talk and say ha, for example, and you hear your sound again, this is the echo. So this is very simply the seismic method. So I send sound wave to the subsurface, and I receive the echoes of this sound wave that reflects back from the subsurface boundaries between seismic rocks. We'll talk about this in details, not today, but in the coming lecture. So the wave, to know the wave element, so as you all know or study in physics or whatever, so we have the wave, the sound wave, we have the amplitude, the maximum excursion of the data, we have the period. If I talk about time, I can see the wave from two types. What I mean, the time or position. Like if you are within a boat in the sea or whatever, and there is like a jet ski or whatever passed by, so there will be a wave in the water. So You can imagine when this wave comes to you or to your boat after how many seconds or minutes, or the distance, between you and the wave. So the time, we have this terminology, which is as amplitude and period. If you go to the position, so we'll have again the amplitude as it is, but we'll have the wavelength. The wavelength is the distance between two successive peaks or troughs and whatever. And how we build this on the seismic data, you see the seismic section in the previous slide. It actually composed of several traces, as we will see next. And these traces contains different colors. The different colors are either peak or a trough. So we have peaks, we have troughs. These are the elements of the wave. So this is what is displayed on the seismic section. So we have peaks and the troughs. We'll understand thoroughly when I have a peak and when I have a trough in the coming lectures. But seismic data actually has a resolution. It has limits to see. The resolution is how thick the seismic method can see, or how thin sedimentary rocks that the seismic can see. It depends mainly on the frequency and the wavelength. So if I go deeper in the earth, I will have lower frequency and long wavelength. So I cannot see the very thin geologic layers, but at the shallow part I can see the very thin geologic layer. How I can overcome that? You can overcome that with the processing, as we will see. So how can we have this seismic tree? So if I have this lithology log, which contains or represent different type of rocks, for example, this will be the seismic trace, peaks and the troughs, as we just said. The seismic trace, we mentioned that the seismic method is sound wave. We send sound wave. So this sound wave propagates in the subsurface according to two main petrophysical or physical rock properties. Number one is the density. So each rock type has different density than the other, and the velocity of sound wave propagation. So when you talk on hard ground, you will have a velocity different than when you walk on a loose ground like the sand or whatever. Okay, so sound also propagate within the rock by different velocities and different densities. Okay, so the main two items that control the seismic propagation are density and velocity. We will see that in the next, again, lectures in details. So suppose that I have a well and I measured a sonic log. So the sonic log can give me velocity, and the density log can give me the density of the rock. If I multiply both of them, I will have what we call acoustic impedance log. Then I will calculate what's called the reflection coefficient. You will know this in details in the coming lectures. So I'll have reflection coefficient, and then I have an integrated log for that. This will be convolved with the waves that I sent from the surface, and I will have the seismic trace. Okay. Because of that, the seismic is a treasure, because it has a lot of information about the rock itself through its density and velocity. The next step is the seismic data processing, and to understand that in quick, this is seismic section that full of traces beside each other. Now, this is before final processing. This is a crude stack, we call. You see after, can you see the subsurface clearly? You may see this one. Okay, but how about this? This is after processing. You can see now the subsurface clearly. Processing steps is tedious job. It's a tedious job, and very intelligent actually geophysicists that work in the processing of the data. All of these you see are different steps to reach the picture you see in your left hand side. Okay, so these are processing, and we'll talk about this in more detail. In seismic interpretation, we have a lot of applications. But for example, if you take a look on this vertical seismic section, you see the circle here. You can see two reflectors, the dark ones, the black ones, okay, are united in a point. This is what we call in the stratigraphic trap as a pinch out. This is the pinch out, so I can see a stratigraphic trap from the seismic data. So if you took a look on these pictures that I just have here, you can see this is a part of a seismic section, and this part you have here faint reflection, but you have here like bright reflectors. Okay, this is what we call bright amplitudes, and this one we call the bright spot. And if you take a look on this one with the green arrow, we call this as a flat spot. And the flat spot actually it's not a subsurface reflector. It's not reflect any rock boundary, but it reflects the hydrocarbon water contact. So this means that in this picture, you see the top reservoir, which is a bright amplitude or bright spot, and you see the hydrocarbon water contact, so you can calculate the volume of your resources in this. So imagine how many reservoirs you have here. All these yellow rectangles represents reservoirs in the subsurface. Going after that to the other geophysical method, which is the well logs. Okay, and from well logs we can interpret or delineate the lithology, the fluids, and we can do the correlation to know how the geology is different from place to place. So we have like a stratigraphic well log interpretation and a petrophysical well log interpretation. In the stratigraphic, we'll talk about the reservoir lithology and phases, depositional environment, and then we can correlate the several wells with each other. In the petrophysical well log interpretation, we talk about the reservoir and fluid parameters. So we can calculate the porosity, the permeability, the hydrocarbon zones, define the hydrocarbon zones. We can know the water and the hydrocarbon saturations. You will have this, what I mean, in details with other colleagues. So in the lithology, you have different type of logs that can give us a clue about the lithology, like the SP, the spontaneous potential, and the gamma ray. But for adding the phases and lithology and phases, we can use the resistivity logs. There are like a method called electrophases. So in the interpretation of the logs themselves, we can identify the electrophases, and this is what I mean. It's a unique combination of the petrophysical log responses. So we can have different characteristics for the logs. Depends on what I mean. It is some of them giving clue about the deposition was coarsening upward. So the particle, what I mean, of sedimentary rock get coarser when I get upward, or finer upward, and each one of them give a clue about the environment of deposition, and also give you some information about the expected type of reservoir or the hydrocarbon or the petroleum system in the area also. This is another integration. Actually, you can end up with knowing the porosity and the permeability from the data in the well logs. And finally, we can integrate well logs and seismic data. I will talk about the correlation at the beginning. We have two different types of correlation, and each one has its application. Either I have a chronostratigraphic correlation. Correlation means that what you see here is that A, B, C, D are four different wells distributed from the surface, okay, and penetrated the subsurface. So we correlate them to know, you see this green color, okay, it is thick here, get thinner, not found in this one, not penetrated in this one, okay. So this is a correlation to understand the subsurface geological distribution, okay, the stratigraphy. So I can use chronostratigraphic, and the chronostratigraphic correlation, I match the rocks with the same age, geologic age, okay? Or I can have a lithostratigraphic correlation in which I correlate the rocks according to their lithologies, okay? But all of this correlation is to know this type of well log interpretation in which I can see what I mean, the subsurface geology. And finally, we integrate, we have a lot of application of integrating the well logs with seismic, because seismic covers a huge subsurface area, while logs, what I mean, penetrate only a small portion, but you touch the rock, your hands, from the drilled wells. Okay, so you can know which reflector in the seismic is corresponding to this rock type or formation. Okay, so this is simply the seismic well type, but it has a lot of applications that you will wonder, and I will show you in the coming lectures. So, for example, you see this is a log interpretation, and this is a seismic data. The yellow one, if I zoom in here, so this is a non-marine deposition, and the blue one is a carbonate buildup. Remember, the carbonate buildup is one of the type of the stratigraphic traps. So you see in the well, you see this in one location. You see this red log, you know this from this very tiny or very small location. But seismic give you the distribution through this section. And this is a 2D section. If it's a 3D, it will give you in the all directions. So you can map with seismic in this situation. So the well log see more details from the geology because it is from the drilled wells, but in seismic you see the majority or the major picture of the subsurface. With this slide, I conclude my presentation. Thank you for your attention, and if you have any question, I'm here to answer any question you have.